Hey, I'm Daniel. I'm here to talk about our journey of turning Chapel's original research prototype compiler into something that can be, on par with modern languages and tooling. So I have a clicker here. It's really fancy. So I guess I'll get started with the state of things prior to this project, really. So the Chapel project started as a research prototype, as part of a research program. And when you're doing that, and when you're just an up-and-coming new language, you have to convince others of your value, right? Like I'm saying, hey, I'm developing a brand new language for parallelism, right? And people will ask, why? And at all times, you have to justify and prove that you are still making progress and that you can do things that other languages can't. When you do that, you really have to move fast. And additionally, although the Chapel team obviously had ideas for what to do, they still, as part of the work, were still exploratory. You were figuring out the exact optimizations, the best language features, and so on and so forth for the language. And so you didn't know what you were trying to create entirely from the get-go. And also, you needed a really fast pace of development. And to do that, a lot of the times you could take quick and dirty shortcuts. And in particular, you could also boil down new features into existing features in the backend, basically. And that's also a good idea in general because the less special casing you do, the more big features can compile down to small features, the more like orthogonal your language is. But it's still, the way that it was done in particular was still motivated by the speed of development, and so led to some trouble and code that might be a little bit hard to understand. So the compiler, as we alluded to recently, used whole program compilation. As far as I understand, though this predates me, I'm not sure if I was conscious at the time that this happened, but this was a decision caused by simplicity. So it's not that we necessarily thought that whole program compilation would be better. It's just it was relatively simpler to do and also made writing optimizations easier. Also, the language was basically boiled down to like 5 constructs. They were like variable declarations, blocks, calls, and that's most of it. So you're getting this very low-level soup of these calls that you're then optimizing. The compiler itself uses global mutable state quite significantly. There's a global list of every single type of AST node. You just append to it whenever you create a new one. And let's see, what else is there? If something can be, so yeah, go ahead.
I'm so sorry. Can I ask questions during? Or
please, yeah. Just
don't want to interrupt her.
No, please continue, yeah.
This just got me thinking. So, like, Chapel versus Codon or Mojo. Codon, I believe, compiles down to LLVMIR. Mojo, I can't remember exactly how they do it. But differences?
So Chapel, I don't know when LLVM became a prominent thing. As Engin mentioned earlier, or Jade mentioned earlier, one of my coworkers mentioned earlier, Chapel originally compiled to C code, right? And I'm not sure if that was just because LLVM wasn't really up and running and usable, or if that was just a choice. It's simplicity. Lots of other languages compiled to C. Haskell, I think, used to be one of them. Today, it compiles to LLVMIR by default, the same as those languages. I don't know the details of how, in particular, Mojo or Codon compile to LLVMIR. They might even use MLIR, which is like the newer stuff. Yeah, okay, so Jade says Mojo is MLIR. But I guess fundamentally something relatively similar now to what they do, which is generate an intermediate representation from a common compiler toolchain and then use that to boil down. And so the parts that I'm talking about are the compiler front end, which do come before that sort of thing. But yes, so yeah, no problem at all. Right. But anyway, as I was saying, the compiler used global mutable state. So if you were going to remove something, or if you're going to optimize something out, you just removed it from the tree. And that is still how compiler backends do things. Like LLVM does passes on the intermediate representation and deletes things when they're not needed. But it's really not very suitable when the thing that you're trying to do is provide tooling, the stuff that Jade was just talking about. It's not very suitable for front ends. And also, the compiler mixed the things that it was doing. So optimization, type resolution, all happened kind of like in phases that were all intermixed. which made it so that you couldn't just say like give me the type of this, because to compute the type of that, you also had to like do some optimizations or do some other things. At some point, you might have already turned your program into static single assignment, which is much more mangled than what the user has written. So the mapping is kind of more and more complicated to go with. And so the idea on the Chapel team then was to re-architect the compiler front end and possibly middle end to help address these concerns, to make Chapel faster. I'll talk more about this. So yeah, there are several goals, right? The compiler needs to scale. So that's how I just started saying, to make the compiler faster. Whole program compilation is great. The architecture is simple. It allows interprocedural optimization very easily, except if you have a giant project, like 150,000 lines of code. Every time you compile that project, you're compiling the whole project, and that takes a very long time. So the idea, you would want to compile the project separately. So this is what's called separate compilation. So get bits of the project compiled, and then put them together at the end, and only recompile parts that need to change. Also, Chapel started a long time ago, but users today want more than just a terminal with white text that tells you the error. They want an editor. They want to use Visual Studio Code. One of the talks recently here was talking about how VS Code was like a super popular demand for one of the technologies that was discussed. And also, in VS Code, when you make changes, you saw it in Jade's demonstration, the fact that it saves on type as you're typing. So the users end up making lots of tiny changes, and you can't just rerun the compiler on that whole file, doing all that whole program compilation, because that just wouldn't be fast enough, and you'd be redoing a lot of work. And finally, at the point that this this effort started, we had learned more about what Chapel is, the patterns that are common to it, the pieces of the language, and so we thought that we could implement them in a more direct, simple, and unified way. And Chapel has always provided some tools. Jade alluded to them earlier in the classic tools column of their presentation. Chapel has provided ChapelDoc, which is a documentation generator a la Doxygen or Sphinx, but for Chapel. And but also, we want other tools to be built on top of the compiler, and we want these tools to be able to make use of the compiler. So the language server that shows error messages, again, that Jade demonstrated earlier. We'd also be able to sometimes write programs that just analyze Chapel code in an ad hoc manner. Like, this is useful for migration or for like asking about what's happening in the wild, saying like, how many people use this feature? How is this feature used? And so on and so forth. To make the compiler do all that work in addition to compiling the code would make the compiler very complicated. So ideally, what we want is to make the compiler be usable as a library. So you can write a whole another program, say, give me the compiler smarts, and do the specific things that you want to do, like generating documentation, doing language server integration. So, creating a language server, which, is a long-running process, does I/O to interact with the editor. So be able to move all that sort of special stuff out of the compiler and into its own tools. And that's what we did. So this resulted in Dyno, which is the Chapel compiler front end as a library. Whoa, I just did something. Great. Okay, that was, screen goes dark. That's pretty scary. All right. So the front end in Dyno, the front end, which is the part that Dyno subsumes, does a few things. It does parsing, so taking the user text and creating a tree representation of the code. It does scope resolution, which isn't a thing in many languages, but is in some, which just figures out what a variable refers to. Like if you say A, it finds you where that A is pointing, like what that A is referring to. And it does type resolution, which is figuring out which function is being called, what the type of that function is, or what the type of what the return type of the function is, and all sorts of other type-based information. And we wanted it to be able to be used as a library. And yeah, that's I already talked about that. And so when you're doing something like this, you lose the ability to take shortcuts that a research prototype was previously able to make. For instance, exiting on error. Like suppose the user writes some completely incomprehensible, completely invalid, like nonsensical code. You cannot crash. You cannot say no, goodbye, assert, and exit. Because the editor, for instance, in an editor, you need to be able to provide the user that feedback and be able to recover and say, like, once the user fixes their code, to carry on. And I like to call this the horrors persist, but so do I. You also want to be able to print errors. So you don't just want to you can't just print errors. Sorry, you want to give errors to tools, but not just dump them to the console. For the language server in particular, this is crucial because the language server uses the standard output and the standard error streams to encode information, and you can't just pollute them with error messages. You also want to pass them along to tools so that they can reason about them and understand what's happening. Again, you also can't use global state, which was used so often in the compiler before, because you can have multiple projects open in your editor. And if you have global state, sorry, that doesn't, there's what global state is going to get merged or just be this weird hybrid of things. You also can't use really mutable state at all, at least in the way that you used to do it before. Because if you clobber some data, right, you cannot reuse it. So if the editor is typing really quickly and making changes, if every time you're clobbering that, you're getting through the whole compiler pipeline and all of that time you're mutating data, you can't go back and get the results before to reuse what you can. And so that's just off the table. It's also not great to do immediate lowering into low-level constructs because the tools might want to reason at a high level. Like the linter that Jade was demonstrating was looking at the co-for-all loops that were nested in each other. You can't, if you lower the co-for-all loops into a for loop and a task on a different, and a transfer of execution, then the tools that analyze the code will have to piece it back together, and that's error-prone and difficult and unpleasant, and you'd have to replicate that work. So we try to keep it high level and to match the representation that Dyno uses to what the user actually wrote. I'll talk about errors briefly. I personally was inspired by errors from different languages when trying to improve the Chapel compiler. My two favorite examples are the programming language Elm and the Rust compiler errors. So these I've taken from other websites that talk about these. These error messages walk you through the problem. They explain what went wrong, why they think it's an error, what you can do to fix it, and so on and so forth. And that's the thing that Chapel strives towards. So in Dyno, we did this by effectively making as many types of errors that the user can run into as possible into individual things. So different types of errors have different representations. They all contain additional information depending on the error to be able to tell the user what happened, what are the details, what can I do. This helps for nice error messages for something like Elm or Rust, or this helps to get error messages like Elm or Rust because those are also specialized to the different error cases that we see. It also makes storing additional data for the errors type safe and convenient because effectively these are all classes. This is like a C++ macro file, which you might not like, but that's what we went with. And also you're able to print different classes of errors differently because they're different classes. So they just have different logic for them. The result, so this is an error that you see in the Chapel compiler today, although you don't see it by default because our users requested very dense errors being experts in Chapel. But if you throw the detailed errors flag, which you can get an error message like this, which I think is closer to what the Elm or Rust examples are. So you say, hey, you're trying to use or import something that's called to look for, except that thing that you're using is not a module and it's not an enum, so you can't use it. So here's the thing that you're trying to use. It's a compile time constant. That's not something that you can use in this context. And here's how here's how you're supposed to use this feature. Cool. And then, like I mentioned, we try to keep the compiler's encoding of the AST to be as close to the user representation of the code as possible. So here we have AST nodes that map very directly to what the user wrote. So if you wrote a reduce operation, which is just like a summation or and all these elements in an array, then you get a reduce AST node. And if you wrote a function call, you get a function call, and so on and so forth. And this way, tools that use this don't have to do this reassembling of the soup of low-level constructs back into something that's usable. And so this is some Python code that checks if an AST node is a loop, and all you do is this a loop? There's no magic involved besides that. And the next thing is, and I alluded to this during Jay's talk earlier, the process of a user writing code in an editor has very different demands from a user compiling the code once. There's very quick changes, and typically they're very localized changes. So maybe you're changing a constant 42 to 17, say. you don't have to re-resolve the whole program. In an ideal world, you could do as little work as possible because very little has changed, and you can just reuse your old information. And that'll make it faster and interactive and just save CPU time. The query-based compiler is an architecture that the Dyno compiler frontend opted for that enables this. The idea is to ask questions about a code base. Say, what is the AST of this file? Or what's the type of the variable X? And the compiler ought to be able to answer these questions in any order that you ask them and independently, but also at the same time reuse the results where possible. So that if you hover over a variable, you can get its type. You can hover over another variable, get its type. And there's no whole pipeline that you have to go through to get all this information in a big chunk. I have a little demo of this, basically. This is a worked example. Here, there's a program with 3 variables, x, y, and z. X and y are just 2 variables. They're equal to 1 and 2. And z is the sum of those 2 variables. I think we can understand what this code does. So here, I also have a dependency diagram of how to compute this information. So to compute the type of z, you need to know the types of x and y, because they're being summed. You don't know what they are. And to compute the types of y and x, you also need to parse the program, because you need to know what they're pointing to, like what's on the right side of the equal sign. You need to know what the user wrote, basically. And suppose I ask, what's the type of x? Well, I can ask what the type of x is, and then I will also have to parse the program. And I shouldn't have to resolve a type of z or the type of y. If the user then asks, what's the type of y? Well, I've already parsed the program, so all I have to do is resolve y. And then if I ask, what's the AST of the program? I should be able to just return the already computed result, because we've done that, we've already gotten that, basically. In some cases, though, you do need to do some recomputation, but you also want to try limiting it. So if I ask the type of z, I will immediately have to compute all the information, right? Because as I said, to compute the type of z, you need to compute the type of y and x, and for all of that, you need to parse the program. Great. Now let's change x to be 42. I guess it was 2 before, or 1 before. So I made the little circle shrink because, in fact, this invalidates by default the information that you already know. All you know right now is the user has changed the program. So then you ask, what is the type of z a second time? Well, we have to reparse the program because the program changed. So here, the circle has reinflated because the information is once again available. It turned green because we had to redo that work. The thing is, though, that the AST of y has not changed. So we don't have to recompute the type of it because all of its dependencies have not changed. So we can bring it back up to date but not do any extra work. The type of x, recomputing the type of x will happen again because its right-hand side changed from 1 to 42. So then that's brought back up to date, and I marked it green to indicate that it was recomputed. And finally, the type of y and the type of x are still both integers, so we don't have to redo the work of resolving the type of z. And so here, we ended up only needing to redo half the work. Well, half in terms of circles, maybe not half in terms of CPU time, but only half the work of what it would have taken to redo this all from scratch. And we talked about separate compilation and query-based compiler architectures. So Chapel is not a language that suits itself well to separate compilation automatically. So languages like C or C++, they have compilation units. They can have forward declarations and basically compile independently given those forward declarations. Chapel can't really do that. But what you can do is save results of these queries into a file, say, and then, or into some kind of database. And then when you're doing this final compilation, just read that database. And since you can compute the individual queries separately, you have something like separate compilation. So we've experimented with this somewhat, in particular for parsing, and our final goal is to get this to work with type resolution as well, which is the slowest part of compiling a Chapel program. As far as I believe it's the slowest part of compiling a Chapel program. Now, as Jade mentioned, all of this is written in C++. That's not great for writing tools. So, and like I mentioned, Dyno is doing the parsing and type checking. It's not doing the code generation, which is the LLVMIR bits or the C bits. But writing tools in C++ is just not as fun. You also like Jade mentioned, there's no standard package manager for C++. So good luck reusing libraries. Good luck, writing code, managing memory yourself, doing all that sort of things. So what we did is build a Python layer on top of this. And then that Python layer lets you ask these questions in a very high-level way, like what's the type of X? Is this a loop? You saw that earlier. And what's the first declaration in this file, say? And on top of that, we built these two tools, Chapel Language Server and Chapel Check. Jade also showed them off. I have a very brief demonstration. I mean, here's the language server. It can show you the errors in your editor. So if you're writing bad code, it tells you. When you hover over things, it finds what they refer to. That's that scope resolution again. And it can show you the documentation for those things. It can do type-based resolution. Jade showed you the really cool example of this. A simpler example is just showing you the integer values corresponding to enum elements. So here, the user explicitly set red to be equal to 1 and cyan to be equal to the value of red plus 10. The compiler can figure out that the rest of the values are 2, 3, 11, 12, and 13. And it can show it to you, so you don't have to guess. And also, like Jade showed you, Chapel Check shows you warnings and lets you fix them. Here are some warnings, like incorrect indentation, whatever. I'm not even going to read through these. There's a lot of warnings. Many of them can be auto-fixed. Okay, so it's not all rose-tinted glasses, puppies, kisses, all that sort of thing. We have trouble. One day, it's fun. So we've seen the troubles from the beginning, but something that really puts this succinctly is an article that I saw relatively recently, and it's kind of fun to wake up and open a tech news article aggregator and read an article that says against query-based compilers when you spend the last couple of years of your life working on a query-based compiler. The quote that I've highlighted here is that the effectiveness of query-based compilers is limited by the dependency structure of the source language. So if your source language has recursion and lots of complicated dependencies, the effectiveness of query-based compilers plummets, or it's definitely harder to work around. And I thought about this, and I thought about these two standard Chapel modules, Chapel Standard and Chapel Base. And as you can see, Chapel Standard imports Chapel Base, and Chapel Base imports Chapel Standard publicly, in fact, so they re-expose each other's declarations. This is a mutual dependency, and it's over. Go home. We can't do this. Not really. We can work around this, but it does complicate the compiler architecture somewhat. So infinite recursion is not allowed without query-based compilers because you will run out of stack space, you will run infinitely, it's undefined behavior in C++. I'm not sure if you care about that. But normally you can avoid infinite recursion when writing code by having something like a stateful set of things that you've checked already, right? So if you're recursing through a graph, you can say, I've seen this graph node before. The problem is that is state. And we just talked about how you cannot use state in this tool, or at least you can't do it explicitly. And it certainly violates the query-based architecture that we've gone for, because queries must not have side effects to be able to be reused. Otherwise, reusing a query would have some effect on the world that we don't want it to have. And so, go ahead. Yes. So there's state that kind of. So the question was, don't you need state to remember what was already parsed and resolved? The answer is yes, for sure. But that state kind of lives in like a meta tracking layer, basically. So the compiler can have state because it needs to, like you said, it needs to know what's been resolved. But the individual questions, the queries, cannot in themselves be stateful because rerunning them would then change the state, which would change the answer, which would mean we can't reuse the cache, and so on and so forth. So there's state, but you can't write your code using that state naively. You can the query-based engine has state, but the queries themselves don't. And so this is the visited set would be part of the query itself, and so it's disallowed, unfortunately. And there's some ways to work around this. Unfortunately, sometimes you will just have to have another query that explicitly computes the dependency graph before doing the computation, so you can identify cycles. It's kind of annoying to have to do that because it's much more work. Another way is to ask the query engine, hey, have we run this query before? Is this query running? This is bad. Just asking that question and making a decision based on this is a side effect, and it will cause problems. However, today we do rely on this because it is much more direct, and it avoids having to create these giant graph analysis problems. Well, not giant, but these additional graph analysis problems to detect recursion. There's also other challenges with the query-based architecture. So sometimes when you're doing some computation, you produce, say, like an additional bit of data as a side effect. And that side effect of that data additionally can be used later. But in a query-based architecture, you can't just save these auxiliary results, because if the user later wants you to recompute this, you need to know somehow where these auxiliary results came from, and that in fact you'd have to compute the original thing that produced them. And in fact, you just get with a really complicated dependency structure, which just is not really easy to implement. It slows down the query engine and so on and so forth. Also, having a query engine has overhead. So last I checked, if you just turn off all the query tracking in Dyno, you get something like a 5% performance boost. So which leads me to say that there's a 5% performance cost to query tracking. In our view, this is acceptable in interactive scenarios because you can save so much work incrementally recomputing, but also it's a little bit unpleasant. And like I mentioned earlier, some usual operations rely on global state or on state in general, which makes it not possible to do them. For instance, the production compiler has a call stack that it currently maintains. So as it's resolving code, it's saying, I'm resolving main, I'm resolving a library procedure, this is the call stack. You cannot maintain that statefully or without state, because these computations, when they're reused, can occur from different contexts and in any order. And finally, to track all errors instead of printing them to the console and re-emit them if the results are reused or if caching takes place is non-trivial, though it's possible. And that problem in particular, we do have figured out pretty nicely. And that concludes my talk. I having gone after Jade, I can just refer to the outcomes of this as the things that Jade talked about, which are these nice editor tools. And I'll take any questions now. Thanks. Go ahead.
How Dyno optimizes your code?
So Dyno right now does not do optimization. It is a compiler front end. So it computes additional information and then produces the intermediate representation that the back end then optimizes. So the parts that Dyno does are more information that's useful for users and useful for lowering to an intermediate representation, but it does not actually do any mutations like optimization. That's handled by a backend that is stateful and not not query based, basically.
Chapel compiler does a lot of optimizations though. Like earlier in the chapter meeting, I gave a talk about 3 of those optimizations. I just recorded and slides should be ready. So I can checking it out. So the compiler does a lot of optimizations. Dyno is just not part of it.
Right. So in this diagram, as you can see, there's parsing and type checking. That's the Dyno part. Code generation is a really broad part of the compiler pipeline. That's where all the optimization happens, and that's kind of outside the purview of what I'm talking about.
But that code generation is like 30 passes.
It's a lot.
30 passes plus what LLVM does. Plus what LLVM.
Yes.
We can imagine such variety or typical RVM optimization.
What's that?
Typical RVM optimization happening here.
Yeah. So in this phase, yes, we create LLVM IR. We run the standard LLVM passes. Yes. Did you? I saw you raise.
Yeah, just a simple question. So, in the last, you said that there was 5% performance.
Yeah, I'll go back to that slide.
So, but what does that mean? Like, so in terms of the time or in terms of memory?
Yeah, that's in terms of the time. I haven't measured memory footprint as much. I suspect it can get quite large, in particular in large compilations. I think Jade is laughing about that right now. Funny. We're working on it. It is kind of a necessary cost if you want to be able to reuse these results over and over again. And compiling the projects that Jade's talking about right now also takes a lot of memory anyway. So it's the high memory demand is exacerbated by having to additionally save extra information. So it can get pretty bad. Yeah.
Can I add to that?
Yeah. Do you want the mic?
That's very much a problem that all front ends have. Like if you've ever run the Clang D, which is the language server for Clang, I mean it just eats memory in your machine because it's caching all of the results.
Every single one of them in VS Code does.
They all will eat your system, and even if I mean, VS Code by itself eats the memory, and then you've got all these language servers eating memory. I mean, you have the same problem. I know Danny uses Vim a lot. Like the language servers eat the memory, and then everything else eats memory. Yeah.
500 megs per language server, and I have.
That's nothing. That is nothing.
That's already like 8 gigs. Yeah. There, right? 10 gigs. Go ahead.
Oh, go ahead. I've asked so many questions.
Please, yeah.
So you were pointing to some person who wrote an article criticizing query-based compilers.
Yes.
So did he also, he or she, give some alternatives?
Yes, there are alternative architectures written about in that post. I believe Alex Kladov is one of the people working on Rust's query-based compiler, and I think that Rust does use a query-based compiler because it doesn't fit naively into the other architectures. I can't quite recall. I think one of the architectures is the one that I talked about with C, where you can have a language where the individual files can be compiled separately. And then you don't need to do any query. You can like recompile individual files pretty quickly, and that's what language servers do. Okay. I can't remember the third. So I linked the article in my slides so that you can go read it. It's a good article, but it's a little, fun to wake up and be sad about your compiler architecture. So yeah, go ahead.
So I have two interrelated questions. First one has to do with what I've seen in like Mojo and Codon. If you go through like their issues on GitHub, it's just like issue after issue after issue, being unable to do like very simple things like decorating stuff in Python. When they're trying to port that language to be as close to Python as possible. Which relates to the second question, which is like, where's the poop? Like, when should I use Chapel? When should I not use Chapel? Yeah, I'll let it there.
Well, this is certainly outside the purview of my talk. So, I mean, with Mojo, people are asking for Python features in a language that's meant to approximate Python, right? And of course, approximating Python is an important goal because it lets developers who used to write Python to immediately get like, JITted or compiled optimizations for their code. Chapel kind of makes you bite the bullet by switching languages to begin with. And, if the question is like, when should you use Chapel? Well, a super good time to use Chapel is if you're about to start writing a new thing, like start writing new code, and you haven't written anything already. Well, great. A greenfield Chapel project is fantastic. You can get performance really quickly. You can experiment. Chapel, it does make it possible to write maintainable and nice code. Less so if you need to do something like interop, right? I mean, like we've talked about interop this entire time. It's just less nice, basically, because you do have to go through foreign function interfaces like with C or other things. You still think you should use it, but it's like less of a yes, you should definitely do it right now. Don't even think about other alternatives. Both of my colleagues have raised their hands. I will just.
I would say that. I mean, I actually slightly disagree in that I think the interop is the best case to use Chapel. Of you have a single locale application written in, pick your favorite language, and you want to make it distributed. I think that right there is the perfect time to use Chapel, because just doing your communication in Chapel versus MPI or Shmem is just so much nicer. That's really Chapel's, I think, biggest strength is the distributed communication. And so in that respect, yeah, you've got a little bit of foreign function pain, but you'll have that in any language. But you get all of the advantages of Chapel's communication, and you can still keep writing your code in another language. And so I think that right there is a good one. In addition, Daniel's greenfield code. Did you want to add to that, Engin?
Yeah, we're doing it, yeah.
We all have opinions, so we are really passionate about Chapel. So I got asked that question a couple of times, but with Julia, like should I use Chapel or should I use Julia? My answer to that question has been, so Julia is for scientific computing, Chapel is for parallel computing. There is a big overlap. But in your application, is the scientific computing part more difficult or is parallelism more difficult? If parallelism is more difficult, go with Chapel. If scientific parts is more complicated and parallelism is relatively easy, go with Julia. So I don't know where Mojo fits or Kodan, even less so. I don't know those technologies that well. But Chapel's power is parallelism. It's designed for parallelism. It's designed for distributed execution. It has a bunch of other nice features. But if all you need is sequential execution, maybe Chapel is not great for you. But if you care about parallel execution, utilization of your multi-core CPU or GPU, then Chapel is a definitely good alternative for whatever application it is my take on it.
Thank you.
So I'm very interested in giving users guidance for the types of applications and, as an extension, the type of parallelism that fits onto different languages. I'm a developer of an abstraction for task parallelism, just like Chapel does more than just tasks, but the problem, what you said, the problem is until you've written the code, you don't know where the hard parts are, right? And you write the science and then you realize, oh, well, parallelizing this is awful. Or the other way around. Writing the science is really hard with Chapel for reasons. Because not everything are loops, right? So it seems like Chapel is more is everything that you can express as loops, in a way, right? Or like distributed, or like kind of like Pegas data, I guess, right? Structured. Yeah, sure. You have that, but can you do? I mean, we're doing like adaptive refinement, for example, right? I guess you can do that, but I wouldn't know immediately how to do it with Chapel, just by looking at the loop structures. So I think the answer is difficult, really. And I'm not going to promote mine, right? It's a different beast, but you I guess, I don't know, trial and error, I guess. Yeah.
Oh yeah, that's definitely a question that is really easy to ask, but really difficult to answer.
Absolutely.
Yeah, so it's more art than science at that point. Like, yes, so yeah.
One general question. You said in the previous talk you talked about the lessons and you have some unit tests you said here. One difficulty I often encounter with this kind of task-based model is unit testing, because in here it sometimes happens, error sometimes happens, sometimes doesn't happen. So you have special unit testing tool for that, or?
So there's not necessarily special testing tools for like that kind of case. The two things that I will mention are, one, there's controls in the language to turn off the parallelism, so you can test just your algorithm. There's something called like a serial block, where you wrap your code in a serial block and everything inside, even if you wrote parallelism, will happen in serial. There's some issues with that, but it's, for the most part, it will let you run your code in serial, so you can ignore the parallelism and just test your algorithm. What that doesn't help with is, finding race conditions and things like that, which, Chapel does some things to protect you from, but, you can still cut yourself. A tool for that is something called TSAN, or thread sanitizer. Chapel works okay with TSAN. I've done some experiments with it. It's something we'd like to do better with, but that will help you quickly identify race conditions. The problem with TSAN today is that it doesn't quite understand our tasking layer, which is a project from Sandia called Qthreads. So TSAN doesn't fully understand Qthreads, and so can see some false positives. But it can identify some issues.
As more background, our tasks are Qthreads, not Pthreads. So we have resident Pthreads on each core. They stay there forever. Qthreads are much lighter weight to create and move around and stuff like that. So we create Qthreads, but then every single tool that you want to use has to understand what Qthreads are, so that they can produce plausible stack traces.
It becomes a problem for profilers and debuggers and so on, is understanding those threading models.
There has been a lot of work by Joachim Potze on.
Do you want this to be on the recording?
Sorry, there has been a lot of work by several groups in Germany. Joachim Protz is, they've been working on like race detection across process boundaries, so MPI, PGAS. I'm surprised they haven't touched Q-threads, but maybe I'm sure they would be interested in a project like this. I think they're very eager to push the boundaries of their tools. It's JOA CHIM P, and then his last name is Protze, PROTZE. Yeah, TZE. Mm-hmm. Yeah, I shouldn't have said it on recording anyway. I mean, if you look for, he has a bunch of papers on this, so they've been doing that for a while. I think that would be cool. And I guess address sanitizer will work just as well.
And so address sanitizer definitely works and works very well. We have nightly testing that runs ASAM.
Okay.
Another one that's really more for Chapel developers than like a user of Chapel is UBSAN, which finds undefined behavior in C. We found a lot of bugs in like the Chapel runtime. Chapel has its own semantics. UBSAN doesn't necessarily help with that. But ASAN definitely can very quickly identify bugs in your Chapel code with memory issues.
Okay.
And it works very well.
Okay.
Any other questions?
In Chapel in general too.
Yeah.
Today.
Yeah. Anything else about Chapel? If you can't tell, we all love to talk about Chapel.
Well,
Is there some sort of special semantics for GPU support, or?
yeah. So Chapel has a general notion. So the question was, is there any sort of special semantics for GPU support? Chapel has a notion of locales, which are an abstraction over something that has, CPUs and memory, pretty much. Normally, a locale is just a node, right? So you can talk about other nodes. We've also added support for nodes to have GPU sublocales. So then, using the same mechanisms of locality that you use for Chapel, these GPU sublocales turn computations that can be run on the GPU into GPU kernels automatically. So if you write a parallel loop and your code is running on a GPU locale, then that loop will, and if that loop can run on a GPU, then it will turn into a GPU loop and run. So there's no you asked if there's special semantics. So, I mean, they're not necessarily special semantics in the sense that locales are a general concept, and they are kind of at the core of how they're like one of the core features of Chapel, basically, that let you reason about where computation takes place and where data is stored. But yes, in the sense that you do have support for GPUs, and when you use those particular types of locales, you get GPU computations where possible.
My question more for the data transfer, because something cool with Chapel is the communication layer. It's quite nice. How does it work for GPU? Is device-to-device communication or data?
So the easiest answer, the easiest big part of the answer is host-to-device communication, which I will address first, right? So, and device-to-host, like back and forth. That is just like writing an array assignment in Chapel. So if you say var b equals a, and a lives on the host, and b the declaration occurs on a GPU locale, that triggers a data transfer automatically. And so that's how if you got a chance to see Jade's demo earlier today, they were demonstrating basically doing this. So copying data from host to device the same way you would copy a normal array. I believe we have support for, is it called NVLink? Yes. For intra GPU communication. So GPUs can access each other's memory basically. I don't know what the story is for AMD GPUs, but same? Okay, great. So in that sense, it works out of the box. You write code, and if the code is across GPUs and NVLink is enabled, you just access the data, and it works. We also have support for unified memory, which was actually the first implementation of our GPU support, because it's so much nicer. You don't have to reason about copying data. You can actually just access that data, and it automatically gets transferred by the runtime or during whatever page faults or something. But it does not perform very well. That's not a Chapel problem. That's just a unified memory thing. Like, someone else. Actually, I think the person that just left called it a crutch. So I think so far we we've seen something similar. Like it.
There was a good talk, I think yesterday.
Yes, yes. I didn't get a chance to see it, I don't think. But yes, there was a good talk on that.
The only content that you should.
Hmm.
Thanks all for stopping by. Hope
Yeah.
you enjoyed the talks.
Yeah. Thanks so much.